Welcome to the electronicsHobbyblog.com. This is our second installment on resistors, resistor circuits. In the first installment, we learned the basics of resistors, what they are, what they do, and some of the various parameters like tolerance, resistance, and power rating. In this segment, we'll look at resistor circuits, talk about Ohm's law, Kirchhoff's current and voltage law, look at how resistors combine in series and parallel, analyze some circuits, and finally conclude with some practical examples that you can put to work right away. After each example, we'll take a look at what happens in the lab so you can see firsthand how the circuit works. Let's get started. Let's start by drawing a simple schematic diagram of a resistor circuit. The standard schematic symbol for a resistor, the American standard anyway, is shown on the right of the circuit and labeled R. The symbol can be drawn vertically, horizontally, or even at an angle, although we usually avoid drawing components at an angle unless we're looking at a specific configuration, such as a delta or a Y. Also recall, a resistor has no polarity and can be drawn either way round. The symbol on the left of the schematic diagram is the standard symbol for a battery. The V indicates voltage. A battery symbol, like the battery itself, has positive and negative terminals indicated by plus and minus signs. The long and short horizontal lines indicate battery cells. The longer line is also used to indicate the positive terminal, while the shorter line indicates the negative terminal. The battery symbol can also be drawn vertically or horizontally. The lines between the components represent wires or electrical connections, and are usually drawn horizontally or vertically with right angles. The schematic represents a completed circuit in that there is a continuous path for current to flow from the positive terminal of the power source, the battery, through the circuit and back to the negative terminal of the battery. When current, which is measured in amperes or amps for short, and represented using the letter I, flows through the resistor, it induces a voltage across the resistor. The end that the current flows into has a positive voltage with respect to the end that the current flows out of. This is indicated by plus and minus signs at the top and bottom of the resistor. This is called a voltage drop because the voltage on one end of the resistor is lower than the voltage on the other end of the resistor. It drops. Current flows from the positive terminal through the resistor and back to the negative terminal, completing the circuit. In reality, positive charges aren't what flow. What really flows is electrons. And electrons have a negative charge. They actually flow from the negative terminal through the circuit back to the positive terminal. But we use the positive flow convention because it's easier to understand and visualize. Ohm's laws allow us to relate voltage, measured in volts, current, measured in amperes or amps, resistance, measured in ohms, and power, measured in watts, so that given any two parameters, we can calculate the others. The basic formula that relates voltage, current, and resistance is that voltage equals current times resistance. We can rearrange that formula to calculate current. Current, I, equals voltage divided by resistance. Or to calculate resistance. Resistance equals voltage divided by current. So given that, and looking at this circuit where V equals 10 volts and R equals 10 ohms, we can calculate I. Remember, I equals voltage divided by resistance, or 10 volts divided by 10 ohms, which gives us 1 amp. Let's look at another example. In this case, we know the voltage and want to choose a resistor value that will result in a 250 milliamp current. The lowercase m means milli, as in milliamps, and 1 milliamp is 1/1000th of an amp. There are times we'll also talk about microamps, and a microamp is 1/1,000,000th of an amp. So, to calculate the resistance from the voltage and current, we rearrange the formula so that R equals V over I, and convert 250 milliamps to amps by dividing by 1,000. So we end up with that R equals voltage over current, or 30 volts over 0.25 amps, which equals 120 ohms. Ohm's law also relates power, current, and voltage. And again, given any two, we can calculate the third. Power equals voltage times current. And if we rearrange for voltage, voltage equals power divided by current. Rearranging for current is that current, I, equals power over voltage. So let's look at an example. Here we see a circuit with a 10-volt battery and a 10-ohm resistor with 1 amp flowing through it. Remember, Ohm's law says that voltage divided by resistance equals current. So 10 volts divided by 10 ohms equals 1 amp. Now let's calculate the power from the voltage and the current. Power equals voltage times current. 10 volts times 1 amp equals 10 watts. Calculating power is important in component selection. In this particular example, a 1/4 watt resistor would literally explode into a ball of flame. Here, we need to choose a 10-watt resistor as the absolute minimum. More likely, we would want to include a safety margin of 50% and use a 15-watt resistor, or mount the resistor to a heatsink to improve its power handling capability. Let's look at a more complex example. In this case, we know the current, but we don't know the voltage. How can we calculate P equals V times I without knowing V? Well, luckily, both of Ohm's formulas are related, so we can substitute values from one into the other. So P equals VI, but we know that V also equals IR. So if we substitute that, we get I times R times I, which is I squared times R. So power also equals I squared times R, or 0.25 amps squared times 120 ohms, or 7.5 watts. Because we can relate the two formulas to each other, given any two values of voltage, current, resistance, or power, we can calculate the others. Here's a handy little graphic that shows you how to calculate any value, power, current, voltage, or resistance, from any other two values. Now that you know Ohm's law and how you can apply it, you can analyze any simple circuit. The next thing we'll do is to look at how we can analyze more complex circuits that contain multiple resistors. Very few circuits in the real world contain only a single resistor and a power source. Real circuits are more complex, so we need to understand how multiple components, in this case we'll stick to resistors, behave when they're combined in series, parallel, or any combination. To start with, let's look at a circuit that combines two resistors in series. In this case, rather than showing a battery, we're just going to show a generic 10-volt power source. It can be a power supply, a solar cell, a battery, really any kind of voltage supply. For purposes of analysis, we can treat them all just like we treated the battery. In order to apply Ohm's law to this circuit, we need to know the total resistance of R1 and R2 combined. Once we know that, we can calculate the current by dividing the voltage, 10 volts in this case, by the total resistance. Well, it's fairly simple to deal with resistors in series. Resistors in series add. The total resistance is the sum of all the resistors in series, and is given by the formula total resistance equals R1 plus R2 plus R3, all the way out as many resistors as you have. So, given that, solving for the current is a simple matter of adding up all the resistors in series to get the total resistance and then dividing the voltage by the total resistance. Let's solve this equation. So we've got 10 volts and then a 10 ohm and 30 ohm resistor in series. So the total resistance is R1 plus R2, or 40 ohms. The current, therefore, is the voltage, 10 volts, divided by the total resistance, or 40 ohms, and so our current is 0.25 amps, or 250 milliamps. So what about when we have resistors in parallel? Well, resistors in parallel behave differently than resistors in series. If you consider our water analogy, right, where we have pipes and water pumps and so forth, two pipes in parallel can carry water faster than two pipes in series. And they carry water faster than just one pipe. So resistors in parallel behave similarly. The total resistance for resistors in parallel will always be lower than the resistance of the smallest resistor. And it's given by the formula, the total resistance, R total, equals 1 on R1 plus 1 on R2 plus 1 on R3, all the way out for however many resistors we have. Yeah, I know that looks complicated, but if you just plug in the values for the various resistors, it's fairly easy to calculate. In fact, in the example where you have just two resistors in parallel, the formula reduces quite a bit, and the total resistance for just two resistors in parallel is R1 times R2 on R1 plus R2. Looking at an example circuit, if we have a 10-volt power source and then two 10-ohm resistors in parallel, we can calculate the current by first calculating the total resistance and then dividing the voltage by the total resistance. So in this example, if we take R1 times R2, 10 times 10, and divide it by R1 plus R2, 10 plus 10, we get 100 over 20, or 5 ohms. So calculating I, we find that V on R, or 10 volts on 5 ohms, equals 2 amps. But real circuits, as we said before, that they don't contain just one resistor and a battery, they rarely contain only series or parallel components. Real circuits contain endless combinations and permutations of components connected in a wide variety of ways. You can analyze the most complex circuits by simply reducing the circuit to a simpler form. And you do that by calculating and substituting equivalent values as we did in the series and parallel examples that we just worked through. Let's consider a series parallel circuit example and use the techniques we learned to simplify the circuit so that we can analyze and solve it. Here we have a 12-volt power source and a combination of series and parallel resistors. A 1K resistor in series with a 1K, 5K parallel resistor pair. So let's reduce the circuit to something simpler that we can deal with. We'll start on the right side of the circuit and reduce the two parallel resistors to a single equivalent resistor. So you'll remember our formula for two resistors in parallel is R1 times R2 divided by R1 plus R2. Or, in this case, 1K, or 1,000 ohms, times 5,000 ohms divided by 1K, or 1,000 ohms, plus 5K, or 5,000 ohms. So the total is 5 million divided by 6,000. Total resistance, pulled out my calculator here, is 833.3 ohms. We can now take that and plug it into the circuit as the equivalent resistance. So we basically remove the two parallel resistors and replace them with a single 833.3 ohm resistor. Now we can calculate the total resistance and then the current. So the total resistance for two resistors in series now is R1 plus R2, or 1K plus 833.3 ohms. And then calculating the current, we take the 12 volts divided by the resistance of 1,833 ohms, and we end up with 6.55 milliamps. So the next step is that we start to expand the circuit diagram back to its original form, and we calculate the voltage drops and currents in each branch of the circuit. First, let's look at the voltage drop across the series 1K resistor. Well, we know that V equals I times R, and we know that the current I is equal to 0.00655 amps. That's 6.55 milliamps. Times 1,000 ohms equals 6.55 volts. Now, if our total voltage is 12 volts and 6.55 volts are across the 1K resistor, then we can say that the remainder must be across the two parallel resistors. So we've got the voltage across the two parallel resistors. It's 12 volts minus 6.55 volts, or 5.45 volts. So now we can calculate the current through each of those resistors. They both have 5.45 volts across them. So for the first resistor, the current equals 5.45 volts divided by 1,000 ohms, or 5.45 milliamps, 0.00545 amps. For the 5K resistor, the current through it is equal to 5.45 volts divided by 5,000 ohms, which is equal to 1.1 milliamps, or 0.0011 amps. So now we've been able to fully solve that circuit. We understand the voltage across each component and the current in each branch of the circuit. In solving the previous circuit, we had to make some assumptions. We made assumptions about how much remaining voltage was across the parallel resistors, and we made an assumption about how the current split between the two resistors. The reason we can make these assumptions is because of Kirchhoff's voltage law and Kirchhoff's current law. Kirchhoff's voltage law states that the sum of the voltages around a closed loop is equal to 0. So essentially, any voltage that isn't across one component must be across the remaining components. So if we consider the example that we just worked through, there are two loops, one on the left side and one on the right. And to apply Kirchhoff's voltage law, every time we go from minus to plus, we add, and every time we go from plus to minus, we subtract. So starting at the battery on the left loop, we go up through the 12 volts from minus to positive, and that's plus 12 volts. And then we go from plus to minus on the resistor, 6.55 volts. So we get 12 volts minus 6.55 volts. And since there's only one other component in the circuit, the remainder has to be there. Let's look at the right loop. There are only the two resistors, and the voltages across them are shown. So if we go around the loop, starting with the resistor in parallel on the left, we go from minus to plus, and that's plus 5.45 volts. And then we go through the other resistor on the right side, we go from plus to minus, so we say minus 5.45 volts. So in each case, Kirchhoff's voltage law holds true. Plus 12 minus 6.55 minus 5.45 equals 0. And for the right loop, plus 5.45 minus 5.45 equals 0. Kirchhoff's current law states that the sum of the currents entering and leaving a node is equal to 0. Any current going in must come out. Makes sense. So looking at our previous example and the currents, picking the node where the three resistors join, we can see that we have 6.55 milliamps through the 1K series resistor going into the node, and we have two currents coming out of the node, 5.45 milliamps going through the 1K parallel resistor and 1.1 milliamps going through the 5K parallel resistor. So again, checking Kirchhoff's current law, 6.55 minus 5.45 minus 1.1 equals 0. But we can work it the other way too. If we only knew two of the currents, for instance the 6.55 and the 5.45, then we know that the remainder is 1.1 and must be going through the other branch. If, for example, we only knew the current in the two parallel branches, 5.45 milliamps on the left and 1.1 milliamps on the right, then we know that the total current entering the node, which is the current going through the series resistor, must be 6.55 milliamps, or the sum of the other two. Using Ohm's and Kirchhoff's laws, we can solve almost any passive circuit, DC and AC. And although we're sticking to DC for these early lessons, you'll learn how to use Kirchhoff's and Ohm's laws in AC circuits as well in future lessons. Let's look at some practical examples where we can apply what we've learned. Let's assume that we've designed a 12-volt power supply, and we want to include a blue light-emitting diode to indicate that the 12-volt output is active. If we tried to apply 12 volts directly across the LED, we'd end up frying it as soon as we turned on the power. We'd release the magic smoke, and it would be gone forever. What we need to do is to reduce the voltage across the LED and limit the current that's passing through it. I wonder what component we could use that would drop the voltage. You got it, a resistor. We're going to put a series dropping resistor in with the diode. Here's the schematic. The data sheet for the blue LED recommends that it be powered with 3.2 volts at 20 milliamps. That means we need to drop the remainder of the voltage across the resistor. Remember Kirchhoff's voltage law? 12 volts minus the 3.2 volts across the diode leaves us with 8.8 volts across the resistor. So we need to drop 8.8 volts across the resistor. So we need to select an appropriate resistor so that we end up with 8.8 volts and 20 milliamps of current flowing through it. So now we can apply Ohm's law. We take 8.8 volts and divide it by 0.02 amps, which is 20 milliamps, and we end up with 440 ohms. We also need to look at the power to make sure that we don't end up with a ball of smoke and fire. So calculating the power, V times I, or 8.8 volts, times 0.020 amps, equals 0.176 watts, 176 milliwatts. Since 440 ohms isn't a standard value, we'll use the next higher standard value resistor, and that's 470 ohms at a quarter watt. Notice that we went higher rather than lower. We'd rather pass less current through the diode than more. Using slightly less than the recommended current will also extend the life of the LED. Using a higher current would have the opposite effect and shorten the life of the LED. Just to be safe, we'll check the circuit using the new resistor value. Let's take a look. So 12 volts with a 470 ohm resistor leaves us an 8.8 volt drop across the resistor at 470 ohms. So that's 18.7 milliamps. So just like we predicted, that's a little bit less than the 20 milliamps recommended. Let's see how that works out in the lab. Okay, let's get started. So I've got our LED circuit that we designed hooked up on the bench, and power supply set for 12 volts. Got a 470 ohm resistor, inserted. In case you haven't seen it before, this is the way resistors, through-hole resistors often come. They come in a reel with paper on each end, and these are rolled up. And you can see, I'm going to try and get close to the camera with these. These are yellow, violet, brown, and gold. And the yellow, violet, and brown indicate 470 ohms, and the gold indicates that it's accurate to 5%. So let's turn the power on to the circuit, and look at that. It lights up like it's supposed to. It's not too bright. We're not burning anything out. We've got the power supply set to 12 volts. If I look across the circuit, I've got 11.9963. And then let's take a look and see how much of that voltage is across the resistor versus how much is across the diode. So if we look across the resistor, we've got 8.76. And if we look across the diode, we've got 3.23. So it turns out that Kirchhoff's voltage law works, right? The voltage across the resistor plus the voltage across the LED is equal to the voltage across the circuit. Now let's look at the current. To measure current, the meter goes in series with the circuit. So we're going to switch this over into the current input, and we're going to switch the meter into DC current mode. And it turns out to be 18.93 milliamps, which is exactly what we designed the circuit to be. Right? We went from a 440 ohm resistor, which would have provided 20 milliamps. We increased it to the next standard resistor size or value, which was 470 ohms. Keep in mind, of course, that these are 5% resistors. So we can actually check that. That's something else that we can look at. Let's power the circuit off. Let's switch our meter into 2-wire ohms mode. Go back into the connector here. And let's pull that resistor and measure its actual value. And there we go. So we had said it's a 470 ohm resistor as marked, and it's actually 464. So, 0.464 kiloohms is 464 ohms. So that's certainly within the 5% tolerance of the resistor. So for our second circuit, we did the voltage divider where we've got the 1 meg ohm load and then the 10K resistor in parallel. And then we needed a 1.51K resistor. Well, I didn't have one, but I'm using my old, I don't know how blurry this is, but I'm using my old Heathkit Decade resistance box, so I can essentially dial up any resistor I need. And I've got that set for exactly 1.51K. The power supply is set to 5 volts. Let's apply power to the circuit. And then let's hook up our meter across the load. And it gives us 3.251 volts. And that's probably because this 10K resistor is not a very precise resistor. Let's check that theory. I'm going to power the power supply off. Like this, and we are actually going to measure the resistance of this resistor and see how close we come. Yeah, you can see it's only 9.66 kiloohms. It's not quite 10 kiloohms. So that's probably why we're seeing that difference. I didn't use a 1% resistor or 0.1% resistor as we specified, which would have got us much closer in terms of voltage. Anyway, we'll go back to measuring the voltage across the load. Power on. And switch back to DC volts. And what we could do, if we were building this for real, given that we've got that resistor, we could tune our adjustable resistor or use a potentiometer. And I'm just basically adjusting the knobs on this. That looks like it's as close as we're going to get is right now. No, we can get closer than that. Close. See if I can hit it right on the head. So that's an example of actually tuning the resistors using the decade box. And if I read the decade box right now, it's set for 4943. So we're never going to find a resistor quite that size, but we could find a potentiometer in the 5K range. Well, that does it for this installment. If you enjoyed it and found it useful, then please give it a like and a share. And if you subscribe, you'll be sure not to miss any new content. Cheers. See you soon.